Hi. Now we have Pablo Trujillo. If I pronounced that right. He's an FPGA designer specialized in the implementation of control algorithms for power electronics devices. And he's also the author of the controlpaths.com blog. And he's going to be telling us about high-speed digital twins. Over to you.
Thank you. Hello, everybody, and thank you for being here, especially because the talk is about FPGA, obvious, but also about electricity and maths. And I think that this will be the reason what made you be here. In this presentation, I want to talk about simulation. But when in this kind of conferences, anybody talk about simulation, we used to think in simulation in the way in which we simulate our circuits, our RTLs, Verilog, VSDL circuits, VSDL designs. However, what I want to show you today is how we can use the FPGA to simulate an external system, a different system. In particular, we're going to see how we can use the FPGA to simulate an electronic circuit, which can be a power electronic circuit, or essentially any system that can be represented by a set of mathematical equations, which is, I think, all the systems in the world. My presentation is done, so we can go ahead. OK, I mentioned simulation, but what I wanted to speak to you today is about real-time simulation. A real-time simulation is a simulation where if I want to simulate 1 microsecond, the simulator will take 1 microsecond or less to calculate the next output of the system. In this kind of simulations, the time is discretized. And what makes this simulation very interesting is that if I have, imagine that you want to simulate the behavior of a power electronic device. And you have an external controller which is running in a microcontroller. If I connect that microcontroller to the simulator, for the microcontroller, everything is real. The microcontroller will see the measurements, will see that the duty cycle of the PWM that it is applying makes things in the model. In other words, it's like the microcontroller lives in matrix. It is an alternative reality, but this time only with inductors, capacitors, and transistors, which is not so cool like the real matrix. I talk about discretizing the time. Discretize the time is I have a system, and I calculate the state or the output of the system at one point. Then the time step pass, and I calculate again the state of the system. Between these 2 points, there are nothing. It doesn't exist. So if I want to simulate a system which is faster than my simulator, what will happen is that the output of the simulator will be different to the real output of the real system. So my simulator doesn't work. This is very important if we talk about power electronics, because today we have some technologies for the transistors that make the system very fast. For example, the gallium nitride transistors are able to switch between 100 kilohertz to several megahertz. So if the simulator is not able of following the speed of the system, ideally it has to be able to run at least at twice of the speed of the system, but ideally we are going to need 4x or even 10x. So that is the reason because we need very fast simulators. It is true that we can scale the frequency of the system. We can make a system that has a natural frequency of megahertz, modify its coefficients in order to make it slower. But we don't have to modify the frequency of the system because, well, we can modify the frequency of the system, but we also need to modify the frequency of the controller. So we are going to have two different firmwares, one for the simulator and the other one for production, which is not ideal. We need, or we have to, ideally we have to use the same firmware for testing and for simulation, for production. Okay, we know that we need to create a high-speed simulator, a high-speed solver. How we can achieve it? Well, the first one is quite obvious. If I increase the clock speed, I can make my simulator faster. If my solver takes 4 clock cycles in order to calculate one step, 1 point, if I multiply the frequency of the clock per 2, I will have 2 more times more points. The last one is also quite obvious. If I need to increase the frequency of the clock, I am going to need fast FPGAs. Regarding the second one, FPGAs, inside, we can find different type of slices. We have DSPs, we have VRAM memories, we have regular, or what I call general purpose logic, which are the CLBs, and some of them are faster than others. In the case of this presentation, when we want to create a high-speed simulator, we are going to need to use the faster resources of the FPGA. It is true that not all the design needs to be as fast as possible, because we also need a configurator, some kind of communication that can be run in a different clock region. Also, since the CLBs are probably the slower elements of the FPGAs, we need to avoid the use of them. If we talk about the solvers of the simulator, the most important block in the FPGA are the DSPs of the FPGA. We can see that here we have one implementation where I create or I calculate the first multiplication in a DSP58 in case of a Versal ACAP, and then I go to the regular logic, but then I come back to the next DSP. This, what we do is that I have a high speed in the DSP58, but then in the regular logic, I will have to face a decreasing of the speed. However, the DSP58 and the 48, 48T, and many other families are able to communicate they have a path directly to the neighbor DSPs. So if I use the implementation of this implementation, I will be able to run in my design at a higher speed. Okay, so now we know how to make our simulator, our solver faster. Then we need a model. Last year, I was talking about this in some conferences, and I presented this method to discretize a model and implementing them into an FPGA. I call this method the direct translation model. It is based on taking the schematic of the power converter, replacing all of the elements by its equivalent math model. This will result in this converter you have here is a back-boost converter. So if I convert this converter into a mathematical model that can be implemented into an FPGA, we can see something like this. This block that you can see here are the inductor, which is a voltage-controlled current source. Then on the other side, I have the capacitor, which is a current-controlled voltage source. Also, we can see the RL, which is the resistor in series with the inductor. This resistor acts as a damping for the resonance. And in this kind of representation, we can see that it is a negative feedback, which makes the system more stable. And it is what this resistor essentially does. However, if we take a look to the other side of the capacitor, the resistor in series with the capacitor acts as a positive feed-forward, which makes the system more unstable. And this is essentially what it does. Also, here you can see the resistor, the load resistor, and the two multiplexers are the two switches that we can find in the real converter. This direct translation model has some issues that we need to improve. The first one is that if we include or integrate some kind of logic between the multiplication and the addition, the synthesizer won't be able to implement the multiplication and the accumulation in the same DSP block. In this case, for example, you can see that we have the multiplication followed by a shift register. This shift register cannot be implemented within the DSP in a regular way. So what the synthesizer will do in order to implement this will be make the multiplication using a DSP 58 or 48 or whatever, and then goes to the logic, implement the shift register, and then come back to the other DSP, or maybe I'm quite sure that the addition will be done with CLBs in the regular logic. If this works perfectly, but if we want to increase the clock frequency, we're going to face timing violation because we are using low speed resources instead of keep all the solver path using the high speed resources. Also, another of the problems that this method has is that if I change the converter I want to model, the complete diagram will change. So I'm going to need to calculate to obtain a different models for the different converters. Okay, so at this point, what I thought is, when I was in the university a few years ago, I remember that my control engineering professor told me about the space state model. Space state model is a mathematical framework that models the behavior of a system by modeling the behavior of each state. And a state is the element that are able of storing the state of the system. For example, in a power converter, we have capacitors that stores the voltage and inductors that stores the current. So this will be the two states that we have in a back-boost converter, for example. The space state model is based on these two equations. The top equation is the equation that represents the evolution of the states in the time. And the second one is the equation that represents the evolution of the output. The states are the variable x, the u is the input of the system, and the y is the output of the system. Which makes this more interesting if we want to implement this into an FPGA is that A, B, C, and D are matrices. So if we take a look to the equation and replace the A, B, C, and D with matrices, we can see that the entire system is based on dot products of matrices, which are essentially MACC operation, multiplications and accumulation. And since there are nothing that will be between the addition or the multiplication and the addition, this will be implemented or the patient root will implement this into the DSP blocks. Also, if one of what we want to control, for example, is one of the states, for example, the current through the inductor, we can make C and D 0, so we are going to use only the first equation. Here you can see what I told you. This is the implementation of a solver, a few lines of the implementation of the solver. We can see that we have the multiplications, which multiplies the A, which is the corresponding value of the A matrix, and the corresponding state. And then in another state, we have the addition of the system. With this method, we are eliminating the dependency of the model, because if I need to change from a back-boost converter to a back converter, I just need to change the values of the matrix. In order to put all of them in practice, I use this board. It's an iWave global board, the IG G57G, which is based on a Versal AIH BE2302. This is one of the Versal parts that is included in the no-cost version of Vivado until now. Also, the board has a 4 GB in memory, LPDDR4, which is used for Linux and also for storing the samples of an embedded scope. The FPGA, the programmable logic of this part, is used for both the contain the RTL of the model and also the controller. And the processing system will be used to configure the model and the scope. Since I also wanted to see the signals in an oscilloscope, I use a DAC board with 2 channels, 16-bit and 33 megasamples per second. The model I use to test all of this is the model of an electromagnet. And I think there is no better place to make a model of an electromagnet. Actually, if I were an electromagnet, I would love to be here. We can see the ideal inductor, but also the parasitic capacitor and the 2 line resistors. In this schema, in this diagram, we can see that we have 2 different states, the voltage in the capacitor and the current through the inductor. Since the solver I implemented is a 4-state solver, we could also add a second parallel branch in order to simulate a secondary behavior or a secondary effect of the electromagnet. What you can see here is the power stage that controls the current that is flowing through the inductor. In order to obtain the mathematical equations of the system, I use this library, which is free. It is a Python package. The name is LCAPI. And this Python package is based on you are creating an SPICE-like netlist, and then it calculates everything, calculates transfer functions, and what is more important for us, calculates the values of the matrices. Here you can see the 2 Jupyter notebooks. The top one is where the transfer function between the voltage input and the current through the inductor is calculated. And then in the bottom side, you have the state equation, and the bottom, the output equation. And here you can see the response of the floating point 64-bit system with respect the quantified and the discretized system, which we can see that we have 50 milliamps when the current through the inductor is 500 amps. The solver flow that I implemented is the one we saw before. It is a CISO. It is for CISO system, single input, single output, and it can solve models up to 4 states. It takes 4 clock cycles per step. And coming back to the DSP58 implementation that we can find in Versal, we can see that the value of the matrix, the corresponding value of the matrix, and the state goes directly to the multiplicator, and then the addition is made in the arithmetical logic unit. So we have access to the neighbor that are also DSPs. So this line will be the fast path in the solver paths. Regarding the power stage can be modeled with using a LUT5, in which we have the 4 inputs of the state of the 4 switches, and then we also have another input, which is the sign of the current, because according to the sign of the current, the input can be changed, especially when we are in some of the dead times of the system. The complete system is, as you can see here, we have the processing system, the NOC, and all of this connected through an AXI4 Lite interface used for configuration, and then we have another AXI stream used for storing the samples and output the samples to the DAC. Here is a picture of all the experiment. And you can see here the response, which is, you can see the evolution of the states. Here are the evolution of the states of the floating point system, the quantified system, and also the output of the RTL, which is extracted from the FPGA. My design has some limitations. The first one is that I use a fixed point solver because it is faster than using a floating point solver. And I needed to use 40 bits for matrices. This results in that the DSP58 only can multiply 27 per 24 bits. So the place and route will use 4 DSPs in order to implement the multiplication. But with all of the limitation, we reach 250 megahertz, and the model is running at 20 nanoseconds. Regarding the future world, we can implement a floating point solver. We can add some of the effects of the inductor, the saturation effect on the inductor, continue increasing the speed of the model using AI engines, and we can even increase the size of the solver in order to implement the bigger models or bigger lumped element model. And that's everything I want to tell you. Thank you very much.
Thank you. Thanks for the talk. Very nice. Any questions? Yeah.
Thank you for the talk. It was interesting. I'm just curious, what's the benefit of doing this over, like, let's say, running the simulation in SPICE or MATLAB?
Because
why do it in hardware?
Real-time simulation. MATLAB is not. It has a package which is able of performing in real-time simulator, but you need an external hardware. SPICE, for example, is not optimized to make real-time simulations. So you need a hardware that is an accelerator that will execute your.
So you have hardware in the loop.
Yep.
You have a real-time simulator of your power supply, and then you connect it to something with a DAC. Is that?
Yep.
That's what you're doing? But you model basically the entire load in the simulation, right? So what are you connecting the DAC output to in the real world? I'm curious.
I can connect that because my model is just an RTL code. So I can connect the RTL code to the DAC driver.
Yeah, I guess so. Like, what do you do with the physical output in your system? I still don't understand the motivation for the real-time simulation.
No, real-time simulation is able of an external microcontroller, for example, is able of talking with the simulation in real time. We don't have to stop the clock at every cycle, for example. We can let the microcontroller run completely free, and what the microcontroller will see is something that is very similar to the real response of a real system. There is no simulator for the microcontroller.
Okay, I think I understand now. Thank you.
It is known in the industry as hardware in the loop simulations. The difference is that you can do it almost for free, just buying the board, or you can pay in order to have a big hardware that implement this. You can pay MATLAB, you can pay any other vendor that actually they are selling this kind of solutions.
Okay, thank you.
Yeah, go ahead.
I have two numerical questions. So you have to run the results of your multiplications because otherwise the size increase. So you have some rounding, and the rounding can make the simulation inaccurate. It can even make the state space diverge compared to the infinite.
You're talking about the width of my.
Yes, so the output of the multiplication, like if you have 40 bits input, you have 80 bits output, and then you have to reduce them back to something for the next iteration, right? Not within the computation, you can keep the accumulation in 80 bits or whatever, but at some point you have to round, right?
Actually, in order to obtain the signals out of the FPGA in the DAC, you need to reduce it to 16-bit. Regarding to reducing you're telling about the size of 40 bits, internal 40 bits.
I'm just, the generic question is, another aspect of the question is why don't you use 24 bits so that it fits the...
Okay, it is because when you have a solver and you need to include an inductor, for example, the discretized value of the inductor depends or is multiplied by the sample time. If your sampling time is too small, what you have are coefficients that are very, very small. So you need, in my case, 30 bits in order to be able to implement this tiny number in an FPGA in a digital way.
But you don't have stability problems in a state space.
With 40 bits, 10 bits for the integer, and 30 bits for the fractional part, no.
Thank you.
Yeah, another question up there.
Thank you for the talk. So I'm a bit confused on your actuator part. So the FMC card that you use for the duck, that's like 16 bits, and you said 33 megahertz or so. So it's rather slow, right?
33 megahertz? No, 250 megahertz.
No. The duck that drives,
yeah,
right? So that is actually
duck
that's slower than your processing. So you must decimate it at one point. So the question is, do you really need to go that resolution that fast, even though your duck cannot even keep up with the data rate? So, and that's one question. And I have another maybe follow up, but maybe you can answer this part.
Yeah, better, because if not, I will forget. It is independent, the speed of the duck to the speed of the solver, because we want to make the solver faster in order to simulate the system better. So 33 megasamples are a very high frequency if we think that on the other side you will have a microcontroller or a DSP. The DSP will take a signal or will calculate the output of the controller at 10 megasamples, 20 megasamples. So it is not the goal to feed the microcontroller with this high amount of samples. The speed of the solver is needed in order to for a better simulation of the system, of a high-speed system.
Okay, then follow-up question on this. This kind of state space modeling tends to assume that this is a linear time invariant system, right? So, but a lot of the times, I don't know if your buck converter has this, but what about the nonlinear effects? So if you have such things, how do you then place this into your model and solvers?
It's what I talked in the last slide. For example, the saturation of the inductor is a nonlinear effect. So you can still using the space state model, but adding some external hardware. For example, in order to simulate the nonlinear behavior of the inductor, you can use a block RAM that the value of the ideal inductance depends on the current which is flowing through the inductor. So if you can fix it using external hardware like I will do, it is better because the space state model is quite easy to implement in an FPGA. If you need to use a nonlinear solver, then you just need to write the code and make a nonlinear solver. Actually, all the systems, if they are not linear, they tend to be linearized in order to be implemented in this kind of systems. Or you can linearize it not in all range, but also in a closed range that you are going to work in.
Any other questions? Yep, go ahead.
Thank you for your talk. And you've mentioned several times that you're using microcontroller which talks to the simulated system. So you validate the firmware on this microcontroller. If you can you mention what the microcontroller is, what the control software is on it, and if you have considered to use FPGA to control the system?
Yeah, you can use an FPGA. Actually, where I work, I do the FPGA that controls the system. But again, the speed you need to control a system. For example, even if your system is switching at 5 megahertz, your control does not need to go so fast. Because usually, if you are designing a power converter, the power converter will have an inductor, will have then a load, which is usually modelized also. So you know the speed you need, and you don't usually need that the controller goes so fast. But yeah, you can use an FPGA. I mean, that's actually what I do in my real life.
Any other questions? Okay. Can't see any. Maybe let's thank Pablo again and go on to the next talk.
Thank you.